Okay, I'd like to now talk about a few other kinds of trees beyond the binary search trees that we've been looking at. And as you'll see, there's quite a forest of different types of trees out there. And so I don't want you to get under the impression that the binary search tree is the only tree. There are many other useful trees. So I'm going to talk about a few of them here in this module. The first one I'm going to talk about is, I'm going to call it the binary codebook tree. I don't know if that's officially its name, but it's just a more general form of a more commonly used tree called the Huffman tree. But first I want to talk about something a little more general and explain it to you. Now, like a binary search tree, a binary codebook tree is also a binary tree, which means that each node can have two children. And we also, like the binary search tree, we retain a left and a right order. So we actually care that we have a left child and a right child. Those are designated as such. Okay. But the difference is we don't actually label any of the internal nodes. So an internal node is a node with at least one child. And then we also call a leaf node, that's a node with no children. So in a binary codebook tree has only leaf nodes labels. The internal nodes do not have a label. But the edges do have a label. So an edge connecting a node to its left child gets the label 0. And an edge connecting a node to its right child gets a label of 1. Okay? So you see that I've drawn that here. And this is what we need to create a code. So we're going to encode the symbols that are at the leaves of this tree with binary bit strings. Now this is a little different from the way, some of the more traditional ways of encoding characters. You might recall that ASCII is one way of doing this. So if I bring up this ASCII table here, I can see that, for example, the letter capital A is this binary string of 8 bits, 0, 1, 0, 0, 0, 0, 0, 1. And they all have 8 bits, okay? And we've just agreed upon this encoding scheme. But here we're going to do something custom based on this tree. And what we can do is create the code by starting at the root and walking down to the node that has the symbol that we're looking for, and just recording the bits that we pass on the way. So for example, A, well, the way we get there, we start at the root, we walk left, 0, 0, and then that gives us the A, okay? B, it's 0 first, then a 1. C, well, I gotta go 1, 0, 0. D, 1, 0, 1. E, 1, 1, 0. And F, 1, 1, 1. So that's our code. So just to give you an example of how we might encode something, we'll learn how to programmatically do this in a moment, but for now, let's just do it manually. So if I had the string faced, well, an F is a 1, 1, 1, A is a 0, 0, C is a 1, 0, 0, E is a 1, 1, 0, and a D is a 1, 0, 1, according to this binary codebook tree. So that's our binary string. I don't have to put the spaces there, but I did that for illustration. Okay. All right, now actually the reason I don't have to put the spaces there, I can actually just give you the string without spaces and you'll be able to decode it, is because a binary codebook tree is generates codes that are known as prefix free. So are prefix free. So what this means is that, so a prefix is any substring that starts at the beginning of a particular string. So example prefixes of, let's say this one, 1, 1, 0 would be 1, 1 and 1. And I guess 1, 1, well, yeah, no, I just will say prefixes are strictly have strictly fewer characters than the full string. So the prefixes of 1, 1, 0 are 1, 1, and 1. So what you notice is I don't have a 1, 1, or a 1 in any of my codes here. Let's look at some of the other ones. Prefixes of 1, 0, 0 are 1, 0, and 0. Well, I don't see a 1, 0, or a 0 there either. And you can actually see by construction of the tree, I will never have any codes that are prefixes of any others, because the only way you could be a prefix is if you were an internal node. That would be like, so a prefix of 1, 1, 0, 1, 1, that would be if I went 1, 1 and stopped, but there's more to go. I haven't gotten to a leaf node yet, so therefore I haven't gotten to an actual symbol. So that's how you see they're prefix free. And that's a very nice property, because what it means is, so prefix free codes are uniquely decodable. So that means that I can start with a bit string like this, and there's only one way that I could decode it from left to right. And I would do that just by following the tree. So 1, 1, 1. Whoops, I reached a leaf node. Okay, now let me jump back up to the root. 0, 0. Okay, I reached a leaf node. Let me jump back up to the root. 1, 0, 0. Reach a leaf node. Let me jump back up to the root. 1, 1, 0. Reach a leaf node. Jump back up to the root. 1, 0, 1. Boom. Okay. So I had no problem going through this from left to right. There was no ambiguity. I was able to just walk down, get to the leaf, jump back up, walk down again. All right, so that's very nice. Just to paint a contrast, let's say that we had this code. So if we have a code that's not prefix free, we can't uniquely decode it. So there are several options for what it could be encoding. So for example, let me say I had the same bit string, but let me mess with the code a little bit. Let me say that the code actually did have a prefix. Let's make A be 1, 1 and B be 1. And let's see what happens when we try to decode this. Well, so I'm going to start with this string here. And even right out the gate, I'm in trouble, because I don't really know whether this 1, 1, 1. So 1, 1, 1 could be an F, right? It could be that code, but it could also be 3 B's or an A and a B, right? Okay, so you can see the problem here. If I decided that, first of all, that was if I grouped those 3 characters together. But I could also just have taken a 1, 1, and then I would really be off. Let me say I decide that the first one's an A. Now the next one, okay, I got 1, 0, 0. Okay, so I think A, C, 1, 0, 0. So now I'm like off by 1. Another 1, 0, 0. A, C, C, 1, 1, 0. E, 1, 0, 1. D. So I think it's act. But even there, so a D is a 1, 0, 1, but I could have decoded that as B. No, I guess 1, 0, 1. I don't see a 0, 1 there yet. Anyway, there are many ways to decode from a not uniquely decodable string, from a string that's not prefix free. So anyway, so these trees are nice in that way, that we can uniquely decode. Okay, but let's start to talk about algorithms for building these trees from a set of characters. So we're going to use a data structure called a deck, doubly into Q, to build these trees. And a deck is simply something where, so I'll just tell you, a deck, kind of like a linked list, and we have O of 1, addition, removal, both from beginning and end to end. Okay. Okay, so let me show you how we can use a deck to construct one of these binary codebook trees. So let's say we had those letters A, B, C, D, E, and F. So what we can do is add the letters one by one to the deck. So we'll keep adding them to the end of the deck. So first there's nothing, then there's A, then we put B on the end, then we add a C, then we add a D, an E, and an F to the end. Okay. So our pseudocode is going to be, excuse me, while, so I guess I'll call this nodes, this deck. Excuse me. So I'll say while the length of nodes is greater than 1. What I want to do is I'll say n1 equals nodes.remove first. n2 equals nodes.remove first. Then what I'm going to do is say n is equal to new node, and I'm going to pair together. So this is pseudocode, so pair together n1 and n2. So I'll say n.left equals n1, n.right equals n2. So that I made a new node where I pair these together, and then I'm going to add n to the back of the deck. All right. So let's see what that does. Let me just kind of hand trace through this and look at the example. So while I have at least one node, or more than one node in this deck, I'll remove the first one. Let me take that out here, and then I'll remove the second one that was there. Now I make a new node, which you can think of as pairing these two, and actually add this to the back of the deck. All right, so this is going to be in the back of the deck. Go to the back of the line. Okay. And so actually what I'll do is I'll take these along for the ride here, because I recognize that actually these have been taken off the deck and turned into children of that. Okay. Now I take this off the deck, out the front, and I take this off, and I pair those together. Oops. So I'll call that CD. So pair those together. I put the new node on the back of the deck, and I keep going. Okay, now I've got my E and my F. I'm going to take those off, and I'm going to make a new node. These internal nodes don't actually have labels, but I'm just, so that we understand what's going on here, I'm giving labels. So E and the F are paired together, and then that new node is added to the end of the deck. Okay, so every time we go through an iteration of this loop, we have one fewer thing on the deck. We're pairing two things together and combining them into one thing. So we start off with 6. We just went through this loop 3 times, and now we only have 3 things on the deck. Okay, so I'll take off the first 2. The first one's AB, the other one is CD. Here's what gets interesting, because actually now I pair A, B, and CD together. These are nodes, so I pair them the same way. And I'll call this ABCD. So here's my new node, ABCD. Pairing those two together. I'm going to put this on the end of the deck. And then I'm now to the last iteration of my loop, where this, this is the first element in the deck, and this is the second element. So I'll take the first element out, take the second element out, and then pair them, and then the loop completes actually. And I know that the last node there is the root. So once the loop is done, last node is the root of the tree. And that's it. So that's how you would construct such a tree. Now I'm going to have you implement that in code. What I've done is I've created some code to randomly sample the 26 lowercase letters as well as a space and a period. And those are all the things we want to encode. Depending on the order that you put them in the deck, you'll get a different codebook. So here I actually put A, B before C, D, and then EF, but I could put these in different orders, and then I would get different codes. Okay. So anyway, I'm going to have you mess with some code for that now.